So the goal today is basically to continue off what Emily and Anthony have sort of set the ground for, which is to give a geometric description of irreducible representations of certain Heisenberg algebras that you get from quasi-projective surfaces or smooth quasi-projective surfaces by looking at homology groups. Yeah, so first I thought I would review what the Heisenberg algebra is and like the representations that we're interested in, because that was kind of something Emily talked about 2 weeks ago. And then we'll look at, basically the rest of the talk will be about looking at Nakajima's description of these representations geometrically. And yeah, hopefully it makes some sense. I was confused by certain things in the text, but hopefully I won't confuse you when I'm trying to describe them. So we'll see how we go. Yeah, but as I said, this is the main reference. This is the only one I really looked at. Yeah, I didn't look at anyone else's stuff. Like I know that Granovsky was also responsible for proving this result, but I hadn't seen the way he wrote it. Yeah, okay, so in section 1, let me just review Heisenberg algebras and their representations. So the way that Emily described things is a little bit different to the way that we're going to end up describing them, but let me just refresh you on what Emily did. So Emily started with a lattice, which was called gamma, and this was a free Z module of some rank. And on this gamma, we had a positive definite bilinear form like this. Yeah, it was also symmetric. Okay, and from this, we immediately transferred over to this H, which was meant to be an abelian Lie algebra. So we tensored up from Z to C, and we gave it like a trivial Lie algebra structure. So this vector space could have been taken as the primitive object, and that's what we'll end up doing today, in a certain sense. But from H, we then went to a loop algebra, like this. Hopefully people remember this from Emily's talk. And then the Heisenberg Lie algebra was almost this, but we had to take a central extension. So there was an extra sort of dimension, which was this boldface 1. So Emily gave the Heisenberg Lie algebra as a central extension. We had this one additional central element, 1, and the notation was H hat gamma. Okay, and let me remind you what the relations were. So we want the boldface 1 to commute with everything. And then the relations, the bracket on the loop algebra part was quite interesting. So a typical element in the loop algebra looks like an alpha, where alpha is drawn from H. So it's like a lattice element tensored up to C. And then you tensor it with some ft inside of like C. So this guy here is inside of like that. Then we have a beta tensor G of T. And the way that we calculate this is you have to look at residues. So first of all, for the lattice elements, we take the negative of the bilinear form of alpha and beta, and then you kind of do the residue at t equals 0 of ft of g prime of t, and then multiplied by boldface 1. So what is this residue? The residue at t equals 0 of anything that looks like this is just extracting the coefficient of t to the minus 1. Okay. And you could alternatively describe, I mean, it might be simpler or it might be more intuitive to describe what goes on if you look at stuff of the form t to the m, t to the n here. And then you know that monomials like t to the n actually topologically generate the loop algebra. So giving those relations is enough. So before I say that, let me remind you what the topology on this loop algebra is. So the topology on the loop algebra, it's enough to give a basis of open neighborhoods of 0. The basis of open neighborhoods of 0, it's given by looking at stuff like a power of t times formal power series over h, right? So n in z. So yeah, the idea is that this is kind of getting smaller as n is getting bigger. Okay, so that is a well-defined description of the topology on this loop algebra. And then we can make sense of the following comment. So then the Heisenberg is generated as a topological Lie algebra by stuff like alpha tensor t to the n, where alpha is in gamma and n is in z, and by our boldface 1. So when I say generated as a topological Lie algebra, I mean, think about generating in the algebraic sense over these elements. And if you take the closure of what you get, then it's the whole thing. So that's what it means to be generated topologically. But then we have to say subject to some relations. Okay, so we have that this is equal to 0, of course. And then we can rewrite what you get with the general f and g above. We can calculate that actually it's a lot nicer. It's just alpha beta, and then the way the residue works out is that you get m coming out, but only if n is equal to minus m. So yeah, this is just something you can check using what we know about differentiation, but it's going to be normally 0. And the only time it's not 0 is when n is equal to minus m. Okay. So hopefully this is all stuff people remember from Emily's talk. This was all there. And I wanted to get up to this point just to say the way that Emily treated things was then to study continuous representations of this Heisenberg. So after you've done all of this, you study continuous reps of this Heisenberg. But a remark Emily made that we're going to rely on is that you could equivalently study something where you're not generating topologically, you're just generating over t minus 1. I think, what's the word I'm looking for? Yeah, you're only allowed to be, so when you generate with the loop algebra, t is allowed to go infinite in the positive direction, but we could actually say we're only allowed finitely many terms in T and T inverse, and then we can study all representations. So as was said by Emily, we can replace the loop algebra by, I guess these are Laurent polynomials, that's the word I was looking for. And we can study all representations of the resulting non-topological Heisenberg algebra. So if you go with the larger algebra, you restrict to the class of continuous representations because that's what's well behaved. But if you look at this kind of smaller object, then you are equivalently interested in all representations. So we're going to do that because that's what Nakajima does. So one other difference that will come up from what Emily has done is that Emily kind of only gave a brief nod towards the super variant of all of this. So you can do sort of very similar constructions, but starting with a super vector space rather than just a vector space. So H was a vector space, but if we work with a super vector space instead, then you get a different object. And actually, I realized that it's kind of hard not to talk about this today because the relations that we're going to end up checking or the representation that we're going to be interested in really relies on the superstructure. Yeah, the relations become a bit different and there are signs involved, which only makes sense if you incorporate the super story. So yeah, I definitely don't have a lot of experience with super vector spaces or super things in general, but hopefully what I'm saying is correct. So let me recount the super variant that we're going to be using. So yeah, the difference is we're going from the topological to the non-topological and then bringing in the super. So it is a bit different from what Emily talked about. Okay, so we will also replace the lattice gamma, or actually the associated vector space, with its bilinear form, with a supervector space. And a supervector space, in terms of its definition, is just a Z2 graded vector space. So it's a V which looks like V0 direct sum V1. And we're going to assume that it possesses a non-degenerate bilinear form like this. So it's non-degenerate, but it also has to incorporate the superstructure. So it's not symmetric, it's supersymmetric. If you want to change the order, you have to incorporate the parity of the things that you're pairing. So this is what we mean by degree. So this is for homogeneous elements. So V and W are, yeah, homogeneous. Yeah, in my notes I've said that V and W are in VI, but they need not be in the same VI. Okay, so we've replaced the lattice by this supervector space. And now we want to see how do we construct the associated Heisenberg superalgebra. So what do we do? So the first step is to construct the analog of the loop space. And then from there, it's, yeah, you kind of have, so we have to bring in T basically, first of all, because that was the first thing we did. We went from H to HT. So the way we do this is to look at the following thing. So I look at V adjoined with positive powers of t, and I also look at negative powers of t, but I exclude the 0th power of t. This is just following Nakajima, and I'll speculate on the reasons for this in a second, but just bear with me. So we have this W, and it has a bilinear form extending the 1 on V. Okay, so we define it like this. And that's obviously meant to mimic the relations that we had above in the previous Heisenberg, except that now we have a different bilinear form. We've got this super symmetric form. And then we just do the following thing. So the super Heisenberg algebra associated with this super vector space V, we take the free Lie superalgebra of W, and I'll just have a remark in a second about what a Lie superalgebra is, but we do this, and then we want the bracket to basically respect or be determined by the bilinear form. So what is a Lie superalgebra? If I describe what a Lie superalgebra is, hopefully people believe that there is such a thing as a free Lie superalgebra. So let me just put a bit of a recollection on this, even though it's not a recollection for me, it's really new knowledge actually. Basically what you want to do is you want to just introduce signs into the definition of a Lie algebra that respect or acknowledge the superstructure on the underlying vector space. So you have two axioms, just like you have two axioms for a Lie algebra. You have super skew symmetry, right? So if I take the bracket of x and y and I want to compare it to the bracket of y and x, you have a negative sign, but then you also have another sign coming from the superstructure on the underlying space. So this is for homogeneous x and y. And then there's also a corresponding super Jacobi identity, which you kind of form in the same way. I won't write that down. But that's what a Lie superalgebra is. And then hopefully it's believable that there is such a thing as a free Lie superalgebra on a vector space. So we form that for W, and then you quotient out by this kind of relation. So hopefully that's not too confusing. The object we get is quite comparable to what we had before. So the remark is, if you have the same superstructure, if the superstructure on V is trivial, so if V equals V0 has trivial superstructure, we almost recover the old Heisenberg. But what's different? What's different is that we haven't got a bold-faced one. We have no bold-faced one, and we have no V tensor t to the power of 0. So as you've seen, the way we've constructed this is we've conspicuously left out t to the power of 0, or a copy of V itself inside. And as far as I can make out, the reason for this is because the representation theory is, there would be no difference in terms of the representation theoretic things that we're going to do if these elements were in there. But that's just my speculation. So maybe someone who's watching knows better, but as far as I could work out, that's the reason Nakajima is okay to exclude these elements. Okay. Right. So the last thing I need to talk about before we move on is to remind you about representations. Try and make a bit more space. Please interrupt with questions if anything I'm saying is not clear. Okay, so the definition of Fock space that we need is slightly different. So yeah, in fact, the way that I'm going to write it will make it look like it's exactly what Emily introduced, but it's going to be slightly different. So we have a representation on the following thing. So Fock space, I'm pretty sure this is exactly the way Emily defined it. We look at the symmetric algebra of V tensor T inverse C T inverse. That's what Emily looked at. Because her generating objects were of the form, like you take a basis for V, alpha I, and then we had these indices n, and I think n ranged over negative integers, which is what we're getting here. So for alpha I, a basis of V, and for negative integers n coming from here, this is giving you a basis of the, like a generating basis of the algebra. An algebraic basis. The difference is that we don't actually mean the symmetric algebra here, we mean the supersymmetric algebra. Okay, so we have a slightly different definition when we're taking the symmetric algebra of a supervector space. What we actually want is we want to take the quotient of the tensor algebra by an appropriate, what we mean by symmetric vectors in this context, or symmetric tensors, is, again, there has to be a sign. Okay, and so this representation of the Heisenberg superalgebra really does see the supervector space structure of V, and that will be important for the relations that we talk about later on. So if there is no one, what is the one that is in the relation factored out? There's no formal one. Yeah, I think that what Kylan has said is correct. I'm not sure why I even wrote .1, to be honest. Except, well, yeah, I guess you have this one coming from the fact that you're taking a free Lie superalgebra. Does that make sense to people?
The free Lie superalgebra is a quotient of the tensor algebra by something, and yeah, so it's the one in the tensor algebra, or the image of the one in the tensor algebra in the free Lie superalgebra.
Yeah, so it's not meant to be a bold-faced one. Yeah. Okay. Okay, so if everybody's happy with these objects that I've introduced, then we can go into the main construction. Basically, the story going forward will be how we choose this V, because obviously the choice of V is very crucial. Once you choose V, you actually get the Heisenberg superalgebra, and then you can also get the Fock space. So V is very determinative in terms of what you're actually talking about. So let me motivate which V we're going to pick. Okay, so we have to go to geometry land now. So X is going to be a smooth quasi-projective surface. And at various points in the talk, I'm going to limit further what X can be, basically because there were parts of Nakajima that I couldn't understand without more restrictions on X. But possibly that's just something that can be surmounted, but I just was confused by. But we'll see. Just in general, think about a quasi-projective surface that's smooth. And we know that we have the Hilbert scheme for each n greater or equal to 0. And the whole time we're going to pass back and forth quite freely between thinking about points of Xn as ideal sheaves. So it will be convenient at various points to think about them as n points or as ideal sheaves. And then the one other thing related to the Hilbert scheme that I wanted to remind everyone of at the start here is that we have a Hilbert morphism. And what this does is it goes from Xn with its reduced scheme structure to Snx, where, remember, this is n copies of X quotient out by the symmetric group. And what we do is we send a Z inside of Xn to the following thing. You want to look at the length of this Zx, which I'll remind you what that is in a second. So this object we call on the right hand side is the cycle of Z. And the length of Zx is meant to be equal to the dimension over C of the global sections of O of Z at X. I think that's what I want to say. Yeah. Is that the correct definition? I think. Oh no.
Yeah, that's right. But in the current situation with X being a smooth surface, you don't actually need to say the reduced subscheme of the Hilbert scheme. It's a theorem in that case that the Hilbert scheme is reduced and smooth.
Right. Okay. Okay. Good. Okay. So what is our V going to be? We want to describe I don't know actually if I said this above, but this is an irreducible representation. So that's why we're interested in it. So we want to describe this pi geometrically in the case that our V is the following. So I guess I should really, to make it a vector space, I should be tensoring up to C or something, but we'll assume that this is over C. Okay, so to do this, we're going to rely on what Anthony has done last week, which was to define operators on homology groups through defining correspondences. So we had this idea about looking at subsets of subvarieties of direct products and seeing how looking at their fundamental classes, you could get from them to operators on homology groups. And so we're going to get those, we're going to define such operators in this way, and thereby get a representation of the Heisenberg superalgebra. So to begin that process, you have to define the correspondences. So that will involve defining certain subvarieties of things we're interested in. Okay, so so yeah, we're building up to getting correspondences at this point. So we want to consider the following things. So we look at PI is meant to be inside of a big disjoint union.
Just to clarify, you have two different pi's going on, and the pi you want to describe geometrically is the Fock space, right?
Yes, sorry about that. There's a lot of pi's in this talk. Yeah, so pi is the Fock space, and then when I write pi sub n, I'm talking about the Hilbert morphism. It's probably an unfortunate notation, but yeah. Yeah. So I look at the following object. What I do is for each n, I look at, I guess n is greater or equal to I. I look at x, I look at the Hilbert scheme of n minus I points. I product with the Hilbert scheme of n points, and then I product with x, and I take a big disjoint union over all n. Right. So this is this object on the right hand side is quite large, and we're going to define the following thing. So pi is equal to a disjoint union over n. So really, the disjoint union over n is just sort of like notation in a sense, where we're always going to be interested in fixing n to a certain degree. So the first two coordinates I have to give you inside of this thing are something in the Hilbert scheme of n minus I points and something in the Hilbert scheme of n points. So that's going to end up being one ideal sheaf containing another, because the correspondence between points and ideal sheaves is sort of inclusion reversing. So an ideal sheaf in here is going to be bigger than something in here, potentially. So we're going to say that I1 contains I2, and then you have a third point which just lies in X. And we're going to say that the support of the quotient is equal to X, right? And so I guess the point here is that this is kind of a non-generic, it's a non-generic situation in the sense that you start with n minus I points here. If you go up to n points, you would think that this support could, in general, grow quite a bit bigger, but it's kind of just like you're adding x I times. I think that that's a right thing to say. Yeah, so this is kind of quite a special subvariety inside of this thing. We also want to define it for I less than 0. And in that case, you just swap I1 and I2 in this definition. So in that case, you start with n plus I points, and you go down to n points. Okay. So we have pi defined for all non-zero integers. All non-zero integers I. And I guess maybe the reluctance to define the case for I equals 0 is part of the reason that we don't have, we didn't have the t to the power of 0 term above. I just realized that. Okay, but anyway, so we're looking at all non-zero integers, and we have projections of the following form. So this is our big space, and we can take a third projection to x. We'll call that pi I. So yeah, a lot of pi's around. This other map is going to be called var pi I. And this is just the projection onto the first two factors. Okay. All right, so the first thing I want to do is calculate something about the dimension of PI, or its dimension when it intersects each of the pieces that form up this big space, this big ambient space. So the dimension over C of PI intersect xn minus I times xn. It's given by this nice formula. It's 2n minus I plus 1. So let me prove this. Okay, so we're sort of thinking about this part now. N is fixed. N is fixed in this expression here. And so how do we form a point in this intersection? Well, you kind of can say you have free choice of I1. Okay. We choose our first point I1 from x n minus I. I'm going to look at the case where I is greater than 0. And we know what the dimension of this Hilbert scheme is. This is 2 times n minus I. Okay, so once you've fixed I1, you can kind of break into 2 different possibilities for I2. So let's have a look at the set of I2 inside of I1. So we have to now choose an I2 in calculating its dimension. Suppose we choose I2, but I2 is not quite general inside of PI. We're going to say that the support of I1 quotient I2 is some x, but we're going to insist that for some x inside of x minus the support of OX mod I1. Okay, so just on its face, we know that a point in here can be such that the support of I1 quotient I2 is any point x. But if we look at this particular additional restriction that x can't be in here, then this turns out to be the maximal dimensional situation. So if you choose x in here, you get something which has the same dimension as PI. But if x were inside of this support, then it's something of lower dimension. So it's enough to sort of just look at this part in order to calculate the dimension of PI. So I guess this is meant to be, this set is kind of generic inside of PI. And this corresponds to an open subset of the Hilbert morphism inverse of the following thing. So you look at SIX, right? So why are we looking at SIX? Because the difference between I1 and I2 is I points, right? I1 was chosen from n minus I points, and then to sort of get to I2, it's like we have to add I points. And the open subset in here is we don't quite want to look at the whole SIX. We want to insist on we want the cycle to be supported at just one point. So we have to put this is the notation. In general, you can put any partition down here to specify what kind of cycle you're interested in. So let me remind you what this notation exactly means. So SI sub IX, obviously this sub I in brackets is meant to be kind of like an extreme partition of I. And you basically have a cycle supported at exactly one point. So this is inside SIX. Okay. And the good news about choosing things in this way is that we know something about the dimension of this pre-image, or at least Nakajima does. In the book, he's calculated what these dimensions are. So something about the Hilbert morphism, the fact that it's semi-small, allows him to know that the dimension over C of this pre-image of the Hilbert has dimension exactly I+1. Okay. So we sort of said that we have this situation inside of P1, this dagger, this subset. And then, as I've already sort of said, the analog of this condition, where instead we say that X is inside of the support, it cuts out something inside of P1 which is of less dimension. So it has smaller dimension, which hopefully is believable because the support is closed. So you're kind of, you're restricting X to be in something of lower dimension. So it has smaller dimension than I+1. Okay, so overall, incorporating the choice of I1, we get that the dimension of Pi intersect Xn minus I, it's equal to the choice of I1 plus this I+1 term, which is exactly what was claimed. Okay, so does anyone have any questions at this point?
Yes, what's the pi whose open subset do you have?
So sorry, yeah, pi is the Hilbert Chow.
So now
Without
it's
subscript.
Ah, sorry, yeah. Yeah. I should have broken the notation. I should have changed it to have fewer pi's around. Yeah, okay. Yeah, okay. Okay, so basically we've introduced these PIs and we've said something about the dimension. So from here, I want to define a couple of extra things. So we want to actually define the correspondences now, which will give us the operators in terms of the PIs that we've got. Okay, so we have, I want to take one class in Borel-Moore homology of X, which is what we call alpha, and then beta is inside of normal homology of X. And we want to consider the following things. So P alpha of I is going to equal the push forward under pi. So remember that we have a triple product, and var pi is the projection onto the first two factors. So hopefully everyone can see my notes if you don't remember the notation. I think I had like var pi subscript I or something, but I'll just suppress the subscripts in these things. And we have something on X, and then pi was the projection to X. So when I pull back, I get something on the triple product again. So that's what this is. And then we can cap with the class of Pi. Because that lives on the triple product. So we're looking at I is greater than 0. And then P beta minus I is going to be this push forward. So similar definition. Okay, so definitely I was mystified when I first saw this. let me just make a couple of comments about the things that are involved here. So the cap product that's here is meant to arise. I think we've determined that it arises via duality from the cup product in relative cohomology. So something we saw with Anthony last week was a duality between relative cohomology and Borel-Moore homology. And that's what's being called on here. The thing that's confusing, for me at least, I mean, is exactly why we have this mix between Borel-Moore and normal homology. So from this point on, it might make a lot more sense to assume that X is projective, because at the end of the day, we want these operators to be defined on a consistent vector space. And the vector space that I think we're working with is going to be this as V, right? So in that sense, we would probably want X to be, at least I can't really understand what's going on unless X is compact and actually these two things are the same. So try to keep in your mind that X is projective. And if you can see a way to understand what goes on if X is not projective, then I'll be very happy to hear about it. So I'm retaining this notation, but really think of these things as being the same, like in the case that X is projective. Yeah, I don't know whether we got any further yesterday talking about it, Anthony, but yeah, I'm confused about why alpha and beta are chosen from different sets.
Yeah, I'm confused as well.
Okay, that's a good sign. Okay, so yeah, think about these as being the same. Okay, so where do these things lie? After you do all of these operations, these end up belonging to the following product over n. So you have n minus plus I, right? So if I is positive, you're actually subtracting. If I is negative, you're adding, which is consistent with what we had above. Like that. But we're going to be mainly focusing on particular n. Okay, so if you look at the intersection of these guys with each n, then you have something in this tensor product, which based on what we saw last week gives you an operation. So let me recall what Anthony talked about last time. So if M1 and M2 are varieties of dimensions D1 and D2, and Z is inside of M1 times M2 of dimension D, so we have these two projections, say, to M1 and M2. And from such a Z, we talked about defining a correspondence, right? So we have correspondences. And the way that these are defined is you go from the homology of the second guy to the homology of the first guy. And what you do is you take a class C inside of the homology of M2. You pull it back. So you look at P2 star of C. Then you cap. So at this point, once you look at P2 star of C, you're up inside of M1 times M2. And then you cap with the class of Z. And then you push forward back to M1. This is the way that these correspondences arise. And so once we restrict to each n, so restricting to each, or actually, yeah, I mean, I guess we restrict to each n and then take a direct sum, so it's kind of not really a restriction, but restricting to each, do I want to say this? Yeah. Well, I want to say, let me just write what I wanted to write. So we have these P alpha I, P beta minus I. They give correspondences of certain degrees, right? So actually, yeah, I should write here, this is degree D minus D2, right? So it's not like the degree is being preserved in this mapping. Right? And so for the same reason, we get correspondences from P alpha I and P beta minus I, but they're not degree preserving. But yeah, we get this direct sum over n because we're looking at obviously something which is inside a direct product over n. Whoops. Yeah. So does anyone have any questions about that?
I have many uncertainties about this, but I think, so one concrete question is that the case of correspondences you've recalled there is where you have an actual subvariety of the product.
Yeah.
These P alpha I's and P beta I's, or P beta minus I's, as you define them, are not obviously of that form. They're not fundamental classes of the subvarieties. I mean, I think if X is, I mean, if you do assume that X is projective and hence compact as a topological space, then I suspect that probably P alpha I, for instance, is just the fundamental class of a subvariety in xn minus I times xn.
So when you say that, like you need like a concrete Z, couldn't you sort of generalize a bit and just say cap with whatever you're dealing with?
Oh, sure, you can. Yeah, I think I said that last time, but yeah. So
I mean, I hadn't written that.
Yeah. So to interpret, to deduce correspondences from the P alpha I's as you've written them, you need that more general form of the definition where you have a class in homology of the product rather than, which is not necessarily the fundamental class of the subvariety.
Yeah. So yeah, you're right. And so I've been sloppy in terms of my recollection. I just kind of wanted to give the gist, which is that if you have an actual Z and you get the class, but I guess the point is that you can get classes of some type and then do the same construction where you just cap with whatever the class happened to be. But yeah, hopefully that's fine. So we have these correspondences, and then the theorem is going to be that these afford us the representation that we want. So at least if we assume one extra thing about X, so this is the theorem that we've been building towards. And I think based on something Emily had said that this was kind of concurrent work of Nakajima and Granovsky. So what we have to do is, first of all, assume something about the degrees of alpha and beta. So suppose that the degree of alpha times the degree of beta is even. And then we have the following relation. So we have that the commutator of P alpha I as an operator with P beta J as an operator, it's equal to -1 to the I minus 1. Okay, so we've got this factor out the front, which I'll say something about in a second. And then we have this Kronecker delta alpha beta times ID. Okay, so this is the part that should look familiar because this is the relation that we had that we described previously. Why do we have this extra sign coming up? This is what comes from the superstructure. So we described the Fock representation before, and Emily's relation for the Fock it looked a lot like this, but because of the additional superstructure, we have this -1 to the power of I-1 coming out as well. The one other thing I haven't described is what I mean by this pairing. So we're wanting to think about V being this from our discussion in section 1. And so the additional data we needed was the supersymmetric pairing. And so this is meant to be the push forward to a point of alpha cap beta. And so when you take this pairing on V, then we're in the situation of section 1 where we can form the Heisenberg algebra and the Fock representation. And what this theorem is exactly saying is that if we ignore this first condition, at least about being even, then we get the Fock representation of the Heisenberg algebra associated to this. So let me write that. So in particular, if we assume, so this is another assumption on X, if we assume that this is concentrated in even degrees, then this big direct sum, which is where P alpha and P beta are operating, it's a rep of the Heisenberg associated to our V, and it has we can also identify what the highest weight vector is. Okay. And so we have some representation, and where it's not clear just from the way that the theorem is stated, from the relation, that this is an irreducible representation, but that is something that Nakajima also proves. Okay, so the remark is that this is actually something that we've already seen. So this rep is an irrep by considering graded dimensions. So this relies on parts of Nakajima's book, which I haven't looked at, so I'm not going to. I didn't want to say anything about this, but this is actually an irreducible representation. Okay.
Josh?
Yeah.
So, should we be using Borel-Moore homology here? So the reason I say this is because if you want this pairing to be non-degenerate, you need Poincare duality, and you exactly have that in Borel-Moore homology. So if X is not compact orientable, then you don't have Poincare duality for normal homology. But so I'm saying that if you don't assume X to be compact, I think you should put Borel-Moore homology here. If you want, again, the this pairing to be non-degenerate.
So you want V to be Borel-Moore, is that what you're saying?
Yes.
Okay, well that's interesting because that's not what Nakajima has, but you may well be right. Let me just have a quick look at the text again.
So where you actually have a perfect pairing is between ordinary homology and Borel-Moore homology. If you're talking about a smooth, non-compact surface. That's to say that Borel-Moore homology is isomorphic to ordinary cohomology, and ordinary homology is isomorphic to cohomology with compact supports.
If we look at the relation that Josh wrote, it's only ever going to be non-zero when I and J have opposite signs. And remember that for a negative number, then beta, the class is supposed to be Borel more, and for positive, it's supposed to be ordinary. And so the only time where this pairing alpha beta is actually relevant is when they're in opposite. And so we can pair, as Anthony just said.
Yeah, but as I said, like, you know, it may be mentally easier to just think about X as being projective from now on, because at least that, to be honest, X being projective is the only case where I fully understand what's going on. So it's confusing to me what V is supposed to be if X is not projective. But let me just recount some of the applications of this fact, which Nakajima discusses. So as far as I know, both of these applications, you know, you can obtain them in other means, but this theorem provides you a nice way of figuring out other things, mainly from prior parts of the text. So let me first talk about this Poincare polynomial. So if you have any variety or manifold, you can form this thing, the Poincare polynomial of Z, and it's the generating function of the Betti numbers of Z. So you look at the following thing, where the Betti number, the mth Betti number is the rank HMZ. And then so what you might be interested in is, let's think about Z being each of the n Hilbert schemes, and then look at the generating function of all of the Hilbert schemes at once, right? So one thing that Nakajima notes is that using the theorem, you can rederive this named formula. So it's called Gauchy's formula, and it's in chapter 6 of Nakajima's book. And it's a really nasty formula, but you can rederive it for the generating function of all of the Poincare polynomials of the Hilbert schemes at once. So you look at this thing here. So it's like a bivariate polynomial in Q and T, and it has some quite nasty closed form, but based on the theorem, in other words, an understanding of this space, you can rederive a formula for what this is. And then one other thing is that for X projective, the theorem can be used to obtain Hodge numbers. So ranks of Dolbeau homology. But yeah, I can't say much about these applications. I'm not sure whether there are other applications that you can find from this. Maybe Anthony or Emily knows more, but these were two nice applications of the theorem that Nakajima at least talks about. So yeah, the rest of the talk is going to be describing the proof of this theorem, some part of the proof, but I thought it would be nice before we actually get onto the proof to sort of work out, to give a worked example. So most of the proof is about proving that this left-hand side equals 0, as Emily said, because unless I is equal to minus j, you get 0 on the right-hand side. So the worked example we're going to look at is a case where you get something non-zero here, the one non-zero case, where I is equal to minus j. So let me go down to that. Okay, so we're going to be working with quite a nice situation. So first of all, let's fix a point x in x. And let's say alpha is the class of big X, right? So remember, alpha is in Borel-Moore, so this is okay. And then beta is going to be the class of the little point x. And what we do is let's take a set of distinct points. So we'll say n points, x1, x2, all the way up to xn. And that's lying, we don't want to choose x. We can choose anything but x for these points. And once we choose these endpoints, we identified with the corresponding ideal sheaf I. So in the notation that follows, we're going to be sloppy about whether I is a set of points or an ideal sheaf. Okay, so let's calculate the commutator P alpha I, P beta. Yeah, actually, I'll just say I want I to be 1, and I want j to be -1 of I. So if you look back to the relation that was posited, we want this basically to give us back I, because I equals 1, so that's one factor in there. And we have also a Kronecker delta, which is equal to 1. And the sign cancels down to 1. So eventually you want this to be just I. Okay, so to calculate this, we need a bit more notation to describe various maps that are involved. So we're interested in x n plus 1 times xn times x, because the first case we're going to be looking at is -1, p -1. We have these two projections, xn plus 1, xn like that. Okay, so let's calculate the first part of this commutator. So first notice that if you look at this operator here, if you plug in the definition of the correspondence, it should be the projection to P1, the pullback of I, and then intersected with this thing here. Okay, so let's run through what's going on. I is a set of n points. If I pull back up here, I get, so this is P2 star of I. If I pull back up here, so P2 star of, let's say, well, let me write as sets. So if I pull back P2 star, sorry, P2 inverse of I, I'm going to be looking at I1 contained in I, and then some point y, such that the support of I mod I prime is equal to y. Hopefully, I'm sorry, this is after I intersect, my bad. I should intersect with okay, so hopefully everyone's happy with that. And basically the effect of this cap here is to insist that the point y that I get is actually x. So when you do this cap product, it's actually bringing you down to the part where y is equal to x. So if you imagine this expression here with y is equal to x, and then you push forward down to the resulting set of n plus 1 points. I'm not managing my space well here, but so in 1, basically what we're doing is we're adding some point y in this situation, And when we cap with this, we're fixing y to be x. So we get okay, so yeah, when you push down to the n+1 point situation, you get the class of the ideal sheaf corresponding to x union your point I, because x was not among these endpoints. Okay, so that's the first part of it. Now we need to apply, the next thing we need to apply here is the p of the class of big X of 1 to this expression. Okay, so let's first see how that acts in general. Okay. So how does p sub big X of 1 act? Okay, so again, we're going to do this sort of set theoretically. So, so in general, for a set, let's say, of n+1 points I prime, what we have is that p big X of 1 applied to I prime, we're meant to be pushing forward by p2 after pulling back by p1 of the class of I, right? So we start with n+1 points here, then we pull back, and then we cap with yeah, I mean, yeah. Like that. I think this is okay. And then we push forward by p2 to xn. Okay. So this will give us n points. So notice that on the set theoretic side, if we want to calculate this first part, p1 inverse of I prime intersect this p1, it's equal to basically a set. So I1 is going to be smaller than the ideal that we get now. So we're up inside of the triple product. And such that the support of I prime prime mod I prime is some point y. Okay, so in general, this set just consists of all possible ideals, I1 prime, I prime prime, and y. But when we intersect here, this is the condition that we get. And then once you cap with this px here, oh, sorry, actually I should say, yeah, because we've got distinct points, we can say that this corresponds to just taking 1 point away from I prime. So it's crucial, actually here I should say a set of n+1 distinct points, I think. Right, so I wouldn't be able to make this identification unless I knew that the points of I prime are distinct, right? So yeah, once you make this choice of I prime prime with this support condition, you know that you're just adding some point y, or sorry, subtracting a point y. And so what we end up getting is I could choose any one of the points to subtract. So my cycle ends up being y and I prime take away any point, like that. Okay. So yeah, hopefully this is believable set theoretically, but to calculate these cap products carefully, I guess something we discussed was that you need to know that certain things are transverse. So I've been a bit sloppy there, but hopefully it's believable that in the operations that you're doing, you're either adding a point or subtracting a point. And yeah, in this case, you can subtract any point, which is why you get this sum. Okay, so in particular, if we compose the things that we've calculated, applied to our I, then what we're doing is we're essentially adding a point and then subtracting any point. So we found that this was the union of I with some point x, and then we're allowed to subtract any point from this. So this is the sum over all y inside of I union x of I union the point x, and then subtract y. Okay, and so of course, one of the summands here will be just the I that we started with. And then on the other hand, we have the situation where you take away one of the other points. So you have x involved, x1, and then you've subtracted some xi all the way up to xn. Okay, and then that's just one of the two composites we have to calculate. We have to calculate what happens if you go the other way, but that's easy now because we know how these operators actually act. So basically, on the other hand, we have something like so what happens if instead you subtract a point and then add a point? So if we first subtract a point, we get something that looks like this. Okay. And then we look at the situation where we add a point to each of these things, because that's what this operator does. This adds a point. We have I minus y take a union with x. And the point is that we're unable to get back to I, right? We can get every other term, but we can't get I. The reason being that y was not viably, can't be viably chosen to be x. So yeah, all of the things that occur here necessarily have x inside of them. So we have I equals 1 up to n of x, x1, leave out xi, go up to xn, and we never got I back. So what that shows you is that when you take the difference of this and this, the only term left remaining is I. Yeah, I mean, maybe it'll be good to draw a picture here. So this is an example of what's going on if we start with 3 points. So these 3 points here are meant to be I that we start with. And then our first operator here is px minus 1. And that adds a point, which is our little x. And then if you apply the operator p class of big X of 1, you then subtract any point. On the other hand, if you start with I and you subtract any point, then you basically end up in this situation here. So obviously we mean sums of cycles when we when we do this. And then if you add the point x, this is what you get. Okay, so the difference is this single term, which is what we started with. So maybe that picture makes it clear what's sort of going on. And I think that this combinatorial kind of description of how these operators are acting is kind of what underlies the proof as far as I could make out. But yeah, let me stop and ask if anyone has any questions about what I've done.
Just a comment that Emily mentioned in her talk, that the generators are often called creation and annihilation operators in the physics literature. And you know, maybe those terms weren't particularly well justified just in thinking of them as operators on a space of polynomials. But I mean, certainly in this way of thinking of the representation, they are literally creating and annihilating points.
Right. Mm-hmm. Yeah.
And an observation, if you were in your annihilating one here, your class was X, the whole surface, so you could remove any point. But if you had been restricted to removing only certain points and that point wasn't there, then your output would be 0. And so if you're asked to remove a point that's not there, you just kill the cohomology class. And so you can see that if you remove enough points, eventually you can't remove any more points. And so no matter how complicated a subscheme you started with, eventually there'll be nothing left and you'll have reached 0.
Okay. Yeah. Yeah. I mean, I was sort of thinking about this in a kind of more basic way, which is it's kind of like sets don't have any concept of debt. You can't remove something that's not there, as you said. Yeah. Okay, so let me move on to describing the way that the proof works in general. And basically, yeah, it breaks into a lot of different cases. So let me recall the relation that we're trying to check. We want to check that the commutator of P alpha I, P beta J is equal to -1 to the power of I minus 1, delta I minus J, pairing of alpha and beta times the identity, for suitable alpha and beta. So again, maybe we want to assume.
There should be an I in there as well. An I.
Ah, yeah, quite right. Yeah. Yeah. So yeah, again, maybe we want to assume that the cohomology, sorry, that the homology is concentrated in even degrees or something like that. But yeah, in general, the degree of alpha times the degree of beta should be even. Okay. So Nakajima breaks his proof into several steps. Yeah, basically things are very different based on whether I and j are positive or not. So the first case is ij greater than 0 or ij less than 0. Or you might have one greater than 0 and the other less than 0. And then you have two subcases of that which he deals with. Either I plus j is not equal to 0, or you have I plus j is equal to 0. And this last case down here is the only one where you get something non-zero, as we've discussed. And that was our worked example above. So just because the proof, I mean, yeah, this last part is definitely the longest part. And actually, Nakajima comments that finding this coefficient -1 to the power of I minus 1 was like, that requires like a whole extra part of a chapter. So this is definitely the hardest relation to check, I think. But yeah, the one that's more tractable, or at least that we can get a flavor of, I think, is this one here. So I'm going to be looking at I and j both positive, and then give you a sense of the kind of things that that he does in the proof. Basically, it's about defining the right types of subschemes to deal with the operators that you want to look at. So we're interested in something of the form P alpha I composed with P beta J and then comparing that to P beta J composed with P alpha I as correspondences. And you want to show that they're the same so that this cancels out to 0. So in that sense, it's kind of, you can sort of see how you could proceed. You want to show that certain things are the same. Okay, so let's just have a look at the proof of case A. Okay, so yeah, I'm just going to write down what I just said. So for concreteness, let's assume actually that we just have both positive. And then we need this to equal 0 as a correspondence on the direct sum of homology groups of the Hilbert schemes. And the way to do this is we'll just like restrict attention to a fixed n. That will be okay. Okay, so assume that n is fixed, and then I'm going to have to describe something set theoretic that will correspond to each of these composites. So P alpha I composed with P beta J. Right, so here's our notation. I need a lot of projections. When you're dealing with a composite of 2 of these things, you have 3 Hilbert schemes involved. So these are our first ones. And then we also need 2 copies of X, because we're going to be keeping track of supports of 2 things. Okay, so I'm going to write Pij1 for the projection to xn1, oh sorry, yeah, xni, xnj multiplied by the blue copy of X. And then we have a red copy of X. So I need Pij2. Yeah, this is the red X. And then last of all, I need Pij, just to go to xni times xnj. Okay, and then we recall that we also have these projection maps. So the Pi lives inside a triple product, and this is just a projection onto the 3rd factor. Okay, so let's write down exactly what the operator is that we're interested in. So as a correspondence, what are the n1, n2, n3 that we're interested in? Because of the correspondence that we're looking at, we're interested in n minus I minus j, n minus j, n. So in our notation above, that's what the ni's are. And then we can say that P alpha I, P beta j, composing them, viewing them as correspondences. The definition that we saw last week, you can unwrap it to write the following thing. So this is just some horrible expression. A lot of cap products. Like that. And then the goal is to think, okay, imagine that I and j are changed. They're both positive. How can we compare the corresponding expressions? Okay, so the relevant thing in set theory to study basically the idea is going to be to try and change these terms around, the term in terms of alpha and the terms in terms of beta, And then we'll see that it's actually, you get the same thing after an appropriate isomorphism. So we need to study the following thing, Pij now. And what we do for that is it's meant to be the following intersection. So we look at Pi. So Pi lives inside of here. And we pull it back to this five-fold product. And then we intersect with the appropriate thing, Pj. So we start with something here and pull back into this five-fold product, and then we intersect them. Okay, so if you work out what that means, it has quite a nice description. You're now looking at three ideals corresponding to each of these 3 points. So you have I1 contains I2 contains I3, and you have 2 copies of X, so that's some points X and Y. And the condition on supports is that the support of I1 mod I2 is meant to be your point X, and then your support of I2 mod I3 is some other point Y. So that's why we have 2 points in the mix. And then there are 2 cases that appear here. You have the nice case where X and Y are different, and then you have the case where X and Y are the same, which is sort of, I guess, singular and of smaller dimension. So we can break this up into two parts. Either X is equal to Y, or X is not equal to Y. And this notation isn't meant to be talking about particular points X and Y, but just like the locus where X is, where these points are not the same versus the locus where they are the same. Okay. And one other thing I want to define is to look at the closure of this thing. So let Pij closure be equal to the closure of this. And then what we can do is we want to start to analyze this thing. And what we're going to do is ignore the alpha and beta part first and understand this cap. What you can find is that the cap of the first part this is equal to the class of this closure, and then plus some extra term. Okay, so this R is basically something inside of the Borel-Moore homology on the lower part, or sorry, the smaller dimensional part, X equals Y. So it's kind of like, you look at this term, you look at these terms here, and you have like some big piece, and then you have a contribution from kind of the singular part, X equals Y. So this is meant to be pushed forward. So I is the inclusion of Pij, where X equals Y inside of Pij. So the moral is that, you know, up to some sort of lower order term, this cap, which is part of what we're interested in, is basically the class of the closure of this Pij X not equal to Y. And okay, so for similar reasons, if we change I and J, we get something which is, yeah, so maybe I should say something a little bit about how to think about this thing. So the idea would be that you start with I1, which is a set of points smaller than the set of points for I2 and I3. And to go from I1 to I2, you kind of add X with multiplicity. So you have to add x I times. So x has multiplicity I, and then when you're at I2, to go from I2 to I3, which is a larger set of points, you have to add y with multiplicity j. That's kind of what this is meant to be describing. So this is kind of like a nice locus, if you like. Okay, and then so we're going to be interested in swapping I and j, because that's what we need to compare. So similarly, what we can say is that I won't, yeah, maybe I'll just write it down so that everyone can sort of see it. So p beta, so if we do the beta first, sorry, I think I'm swapping this incorrectly. Yeah, this is going to be p13 star, p12 upper star of pi, and then alpha and beta are interchanged. Oops. J sorry, I think I had these the wrong way around. Yeah. Okay, so basically alpha and beta have changed position. And we also have a similar expression for yeah, I've totally got my indices the wrong way around, I think, here. Yeah, this is okay. Yeah, so I should be writing pj, maybe. Sorry, I think, yeah, I think maybe I meant to write this. But then that's what I already wrote. Maybe this is really meant to be j. I think this seems more correct. Okay, so we're just meant to be swapping I and j. So I get ji plus the push forward of some extra contribution from where x is equal to y.
When you swap the role of I and j, you need to change the value of n too.
Yes, that's true. Yes. Right. Okay. So maybe I shouldn't have. Maybe I shouldn't be changing the notation, but it's like p. One of the p's means something different. Then is that what you're saying?
Yeah. Because we should land in n minus I instead of n minus j.
You're right. Okay. So probably I shouldn't have. Yeah. Okay. So sorry. Just to confirm what Emily is saying, we have n1, n2, and n3 like this. And I think that n2 is meant to, yeah, as Emily says, it should be n minus I here. So actually the notation looks the same, but maybe I should put primes on the projections or something. So we have n1 prime, n2 prime, n3 prime is n minus I minus j, n minus I, n. Okay. So probably what was there before was correct. But if you need to have primes on the projections, perhaps?
Something like this.
Yeah. Okay. Yeah, I think it's okay if we put the primes. So you just need to change the definition of n2. I mean, it has to be, right? Because of the way that's defined. It's, you're just swapping I and j in some sense. So the swap in I and j, when you swap I and j in this definition, the only time it matters is in the middle, right? Yeah. So if I just copy this exact thing, but with my primes on all of the projections, then it should be okay. Okay, so we change the projections to incorporate the swap of I and j. And so we get this kind of thing. So we have some R prime, which is lying in here. And this is meant to be, whoops, this is meant to be some inclusion. PJI, where x equals y, including into PJI. Okay, so I'm aware that it's 11. 5 minutes and I'll be done. I just wanted to show a really nice picture at the end to describe what's going on. So we're at the stage where we know that these terms differ basically by the difference between these contributions, and we want to say that these are basically the same. So we have to have two claims now that will get us to the end. Okay. So the first claim is as follows. So the claim is that this is the claim that's pretty. So there is an isomorphism. If you look at the locus where x is not equal to y, or actually, yeah, it's even better than an isomorphism. It's a commutative triangle. So you have Pij where x is not equal to y, and then there's an isomorphism that swaps I and j. So you have Pji where x is not equal to y, and then it commutes over the projections. So you have two projections to x, pi1 times pi2 or pi2 times pi1, like that. So you have an isomorphism between these things that swaps pi1 and pi I and pi j. And then the second claim is that we have basically the part of the expression for the correspondences that we have, which involves this contribution from the lower dimensional thing, is 0, right? So we care about this because the remaining term in the cap product that we care about is exactly like this kind of thing, which is a contribution plus the class of the closure of this thing, right? And we also have the same for the other one. So this is equal to 0. So the point is that the content of claim 2 is that the lower dimensional contribution is nothing. And so now, because of this being nothing, you just care about, what's the cost of sort of swapping alpha and beta, right? So let me just say why, given the claim, we're done. So given the claim, the result follows. So first of all, you look at something like P13 and this is all you have to look at because of claim 2. You look at this cap pi1 star beta cap pi2 star alpha. So this is exactly what we're interested in because of claim 2. Then claim A tells you how to swap these things, or rather that you can swap these things. Yeah, probably I need a prime here. So I can swap I and j, and that swaps pi1 and pi2, or I'm sorry, yeah, I've been calling them pi I and pi j. So we get pi, pi2 star, pi I star at beta. Which is equal to, now you're just interested in swapping alpha and beta. To get the expression that you had on the other side. Yeah, I'm worried that I've mismatched. Yeah, I think, yeah. Maybe this is what I should have done, yeah. Yeah. Right, so we know how to commute cup products, and you get this factor coming out because the cup product is super skew symmetric. And what we know is that these outer terms agree with P beta J, P alpha I, and P alpha I, P beta J, respectively. Up to the sign, I should say. Okay, so just to finish off, let me give you a nice picture that describes why claim A is true. So we have a nice description of this thing, and we have a nice description of this thing, and let's see why there is this isomorphism going from here to here, which swaps the projections. Okay, so this actually ends with a nice picture, so let me give you the proof of claim A. So what does a typical point in the left-hand side here look like? It looks like I1, I2, I3, XY is inside of Pij, and X is not equal to Y. Then what do we look like? We look like we have I1 is inside of this Hilbert scheme, I2 is inside of Xn minus J, I3 is inside of Xn, and we saw that the support of I1 mod I2 is our X, different from our Y, which is the support of I2 mod I3. Okay, and what we want to do is kind of copy this definition to see what we get if we swap I and J. Okay, so if I swap I and J here, then as we said just before, we need to write n minus I here. Okay, so this is what happens if we swap I and J. And so the question is, how do I define a map from data of this kind to data of this kind? Well, we're okay to just send I1 to I1 prime, where I1 prime is the same as I1. We can sort of fix this first part, and we can fix this last part. But the difference is, how do we go from I1 to I2? We have to add I points. We have to add X I times. And then to go from I2 to I3, we have to add Y J times. Okay, so the description of this kind of data is to add X I times, then add Y J times. Okay, whereas over here, it's like we're adding Y J times. Sorry, no. Yeah, I think that's what I wanted to say. So sorry. So we want to add J points, then add I points. Okay, so basically I2 is meant to satisfy the following two equations. I1 mod I2 prime is I2 mod I3, right? And I2 prime mod I3 is equal to I1 mod I2, right? So it's basically about the order in which you add the points. So these two equations will be transparent when I just had this picture. So this is our I1, which is common. And then we're going to add, so we have I2, we've added the red points. And then with I3, we've added the blue points, and they have different multiplicities. So in this case, you might have I equals 3, which are the 3 red points, and then j equals 2. So you add the 2 blue points. But then a different way to get to I3 would be to first add the blue points with multiplicity 2. So you add j points and then add the I points, right? So this is how you get the bijection from I1, I2, I3 to I1, I2 prime, I3. So the map between this kind of data is what I was calling tau ij. And you can describe exactly what I2 prime is, because the difference between this and this is meant to be the difference between this and this, which is what this equation says. And on the other hand, the difference between this and this is the same as the difference between this and this. So actually you only need the first equation to specify I2 prime. But anyway, now you've got this correspondence tau ij, which sends you from Pij where x is not y to Pji where x is not y, and it clearly commutes with these projection maps. Yeah, so I thought that was quite a nice picture. I should definitely end now. Yeah, I think the rest of the proof, where you have I and j maybe of different signs, proceeds by defining clever varieties like the Pij, and then performing these kind of calculations to show that things cancel out, or in one case that you have something non-trivial on the other side. So yeah, thanks for bearing with me. And yeah, that's all I wanted to say.